Hello, this is Eileen Solomon. Today we're going to discuss some of the methods of solving higher order differential equations. And we're going to review the basic techniques of solving just differential equations, not systems, on this video. All right, so the first thing that we learned in this unit was the importance of finding linearly independent solutions to a second or higher order differential equations so that we could write a solution, a general solution, as a linear combination of those. All right, so one way that we can determine whether functions are linearly independent on an interval, then we use the Wronskian. And if you recall, the Wronskian is simply a determinant that involves those functions. If the Wronskian is not equal to 0 for all x in the solution interval, then we can say that those functions are linearly independent on that interval. All right, so let's look at this example. Are the functions y1 equal e to the 2x and y sub 2 equal e to the 5x linearly independent for all real x, or we could say on the interval from negative infinity to positive infinity? So we set up the determinant of those two functions with y1 and y2 in the first row, and the derivatives of y1 and y2 respectively in the second row. And of course, the determinant of a 2 by 2 matrix is the left diagonal product minus the right diagonal product. So that gives us 5e to the 7x minus 2e to the 7x, which becomes 3e to the 7x. And since e to a power is always greater than 0, we know that product is always greater than 0, which means never equal to 0. Therefore, those two functions are linearly independent for all x. So if we solved a second order differential equation and we got those two functions as solutions, then we could write our general solution to the differential equation as y equals c1 times e to the 2x plus c2 times e to the 5x, which is, of course, what we're looking for. All right, so the next thing we did was we learned how to solve homogeneous linear differential equations that have constant coefficients and are of second order or higher. So the technique that we used was to basically make a reasonable guess as to a possible solution that would work, and we assumed that y equal e to the mx was a solution, again assuming the independent variable was x. If the independent variable is t, which is the case in a lot of problems, then our assumption is that y equals e to the mt would be a solution. So once we substitute y and its derivatives into the differential equation, we know we get an auxiliary equation that just has m in it. We solve that auxiliary equation for m, setting it equal to 0, and find the roots. And then what we do as far as writing our solution depends on what kind of roots we get for m. So case 1 is that if the roots are distinct real roots, m equals r sub 1, m equals r sub 2, etc., then we would simply use a linear combination of e to the r sub 1x. So y equals c sub 1 times e to the r sub 1x plus c sub 2 times e to the r sub 2x, and so on, depending on how many roots you have. That requires that each of those roots be different and real. Okay? The second case is that we might have repeated real roots. So if I have m equal r sub 1 as one of the repeated real roots and it has a multiplicity of n, then we would have to include y equals c sub 1 e to the r sub 1x for the first occurrence, and then y equals the second term, of course, would be the plus c sub 2 times x e to the r sub 1x, so that those two solutions are linearly independent, plus, and then we keep going until we have n terms. Each one of the next solutions has to be x times the previous solution that we got. Okay? And we could have a combination, of course, of these, and we're going to look at some examples of those on the next slides. If the equation has non-real roots, m equal a plus or minus bi, which we know the non-real roots always occur in conjugate pairs for polynomials that have real coefficients, then our solution from Euler's formula becomes y equal e to the ax for the real part times the quantity c sub 1 cosine bx plus c sub 2 sine bx for the imaginary part. So remember, that comes from writing e to the a plus bi times x as e to the ax times e to the bix. That gives us the two solutions. Remember, this solution is the same as bringing the exponential in front of the cosine. So, you could think of it as two functions, e to the ax times cosine bx and e to the ax times sine bx, but it's fine if you just want to leave it as a product. All right, so now we're going to look at some examples of actually solving differential equations with each of these three cases. So example 2 on this particular video is the third order differential equation shown. Y triple prime minus 3y double prime minus y prime plus 3y equals 0. If we assume that our solutions are of the form y equal e to the mx, and we substituted that y and its derivatives, we would get the differential equation turning into a polynomial m cubed minus 3m squared minus m plus 3 equals 0. Okay, we need to solve this equation to find the values of them that make this true. This particular polynomial, cubics, can sometimes be factored by grouping, and this is one of those that can. If we factor out the GCF of m squared from the first two terms, and we factor out the -1 from the last two terms, now we've got a common binomial factor of m minus 3. So if we pull out that binomial factor of m minus 3, then we have left m squared minus 1 as the remaining factor, which of course, when we set each of those equal to 0, setting m minus 3 equal to 0 gives us m equal 3. Setting m squared minus 1 equal to 0 gives me 1 and -1 as distinct real roots for that particular polynomial. So we're going to have three linearly independent solutions, and the general solution will simply be y equals c sub 1 times e to the 3x plus c sub 2 e to the 1x plus c sub 3 times e to the -x. Okay, so that is the solution to the differential equation. So because when we wrote our auxiliary equation, which is what this is called right here, when we set our auxiliary equation, equal to 0 to solve the homogeneous differential equation, the right side is going to be 0 here. Then we simply find the roots. Since they're distinct real roots, we got our solution. That one's pretty simple to do. All right, now example 3 is the case where we have repeated real roots. Now sometimes when you're working high degree polynomials, like this auxiliary equation will be, you may have to use the graph to help you to find the possible roots. And let me correct this, because that's supposed to be y equal e to the mx. And then we're assuming that the solutions are going to be of that form, leading us to the auxiliary equation m to the third minus 6m to the second plus 12m minus 8 equals 0. And this will not factor by grouping no matter how hard you try, so you should pull up the graph, and what you see for this cubic polynomial, which is really not unusual at all, is that at x equal 2, when you graph it as a function of x, you get what looks like a flattening graph at the x-intercept of 2, which of course means that that x-intercept is actually a root 3 times. If it just crossed the axis like a line, then it's not repeated, but this one is, and m equal 2 is the root 3 times. Now if you want to verify that, you can always use synthetic division, remember, and start your dividing, listing the coefficients of the polynomial on top in order. Then we bring down the leading coefficient, multiply and add, multiply on the diagonal, add on the vertical, And since we do get a remainder of 0, we know that m equal 2 is a root. And so if we were going to factor, this is m minus 2 times the quotient m squared minus 4m plus 4, which factors as m minus 2 squared here. So this becomes m minus 2 quantity cubed equals 0, which does verify the 3 repeated roots of m equal 2. All right, so based on that repeated root, our solution will be written y equals c1 e to the 2x for the first occurrence, and then plus c sub 2 times x e to the 2x for the second, plus c sub 3 times x squared e to the 2x for the third. And this is the general solution to the differential equation. And I always like to circle those solutions on a test paper in particular so it's easy for your teacher to grade. Okay, so we've got a case of repeated row roots. We've done a case with distinct row roots. So now we're going to visit the case where we have non-real roots. So again, making the assumption that the solutions are of the form y equal e to the mx, this leads us to our auxiliary equation m squared plus 6m plus 13 equals 0. Since that's a quadratic, this one is pretty easy to solve by completing the square or by using the quadratic formula. It doesn't factor. But completing the square works really well when you have a leading coefficient of 1 and a middle coefficient that is even. If I didn't have that, then I might just go directly to the quadratic formula. So to complete the square on the left, we would need to take half of b and square it and add that to both sides. So half of 6 is 3. 3 squares 9. So we're adding 9 to both sides. And we factor the left side as a perfect square. And if that doesn't check, then you've made an error you need to find. And then do the arithmetic on the right. The next step would be to use the square root method, which tells me m plus 3 equal plus or minus the square root of negative 4. Isolate m, and as you do that, simplify the radical. So the square root of negative 4 is written square root of 4 times the square root of negative 1, which is 2i. Okay? So whenever we get conjugate non-real roots like this, we just take one of them. We always want to use the negative 3 plus 2i, and we write our general solution, y equals e to the negative 3x for the real part times c1 cosine 2x from the imaginary part plus c sub 2 sine 2x also from the imaginary part. And of course that comes from Euler's formula. And we know we do not need I in our final solution. We are looking for real solutions, real function solutions to the differential equation. And even without the I, these both work. So if you checked y equals e to the negative 3x cosine 2x, by plugging it and its derivatives into the differential equation, it would be a solution. And if you checked y equal e to the negative 3x times sine 2x, by substituting in it and its derivatives into the differential equation, that would also be a solution to the differential equation, even without I. All right, in example 5, we have a fourth order differential equation, which typically is difficult to solve a fourth degree polynomial. So this again is one of those places where you're going to need to either use the graph or use synthetic division to find all of the roots. So if we begin as we did before, assuming that our solutions are of the form y equal e to the mx, then the auxiliary equation we get is m to the fourth minus 3m to the third minus 2m squared plus 2m plus 12 equals 0. Okay, that fourth degree polynomial is going to require looking at the graph or using the rational zero theorem to find the zeros. If you're allowed to use technology, the graph is certainly one easy way to find the rational roots that are exact, and we do need exact values here. So from the graph, I found that m equal 2 and m equal 3 were visible on the graph. The remaining zeros or roots I'm going to have to get using algebra, because this is all I can see. So the x-intercept of 2, the x-intercept of 3 are visible, but remember, this is a 4th degree polynomial, so there have to be 4 real roots, either repeated roots or we might have some non-real roots. They're not necessarily all real. So let's start with the ones we know and use our synthetic division process to try to find the remaining roots. Those of you who are allowed to use technology like the TI-89 or the TI-92, you could use your C0s function, just entering C0s and then typing in the polynomial, comma, and then the independent variable that you use, close paren, and press enter, and it'll give you all the zeros, including any repeated zeros. Alright, so doing my synthetic division process, I should find a remainder of 0 when I divide the polynomial by m minus 2, which is what I'm doing here, and that did work. So we know, yes, 2 is a 0 as it appeared from the graph. Now I'm working with the quotient polynomial, and the next x-intercept I saw was x equal 3, so when I bring that leading coefficient down and multiply on the diagonal, add on the vertical, multiply, and add, block off the remainder. Now 3 is also a 0, as we knew from the x-intercepts. So our remaining quotient is m squared plus 2m plus 2, and we need to set that equal 0. It does not factor, so you're not going to have real roots here. You're probably going to have imaginary roots. So let's complete the square again. So if we move the constant to the right and then add half of b squared to both sides and factor, we get m plus 1 quantity squared equal -1, and this is going to lead us to n equal -1 plus or minus the square root of -1, which we would call I. So we'll add those to our list. So there's our 4 roots, 2 of them real and 2 of them imaginary. So it really does not require a whole lot of work to go from here to our general solution. We have 2 distinct real roots, so we take care of those first. Y equals C1, e to the 2x, plus C2, e to the 3x. And then for the non-real roots that remain, we just need a plus e to the -1x to take care of the real part, times the quantity, C3 cosine x, the coefficient of x here in the angle is the coefficient of I, plus C4 sine x. Sorry, this is a little crowded, but I think it'll work. All right, so that is the general solution to that 4th order differential equation. All right, so those are all 3 cases plus a mixture. So now we're going to go into the technique that we learned for solving non-homogeneous linear differential equations. Usually they have constant coefficients on the left, but that is not required for this technique. If you can find y sub c, then provided the functions on the right side of your differential equation that's not 0 are of the form either e to the kx, sine of, technically it could be kx plus q. You could have an angle involving a sum, although you rarely see that, or cosine of the same type of angle, kx or kx plus a number or minus a number, or sums and differences or products of these functions. Now these types of functions are called UC functions. So if the right side of your differential equation is made up of UC functions, then the method of solving is called the method of undetermined coefficients to work with the right side. So what we want, based on what we learned in the first part of this chapter, was that this solution is really in 2 parts. We first have to assume the right-hand side is 0 and solve it as if it were a homogeneous differential equation, and we call the solution to the homogeneous part y sub c. So instead of having a y equals, we'll just have a y sub c equals, and that's where our arbitrary constants will be and our roots of the form e to the mx that we already learned in the previous examples. Then the method of undetermined coefficients is used to find y sub p. So the technique that I like that works consistently is to write a UC set for each function on the right side of your differential equation. In the UC set, you will list the function itself and all of the functions involved in the derivative process. And if there's not a finite list of functions in the derivatives of that function that you're working with on the right side, then you do not have a UC function and you can't use this method. It has to be a finite set of functions involved. All right, and then do the same thing with the next function on the right-hand side and repeat that for each separate function you have on the right. Then you're going to check to see if one function's UC set is a subset of another, then just scratch it through because you don't need it twice, okay? Also check, once you've gotten rid of the duplicate sets that are subsets of one another, then you're going to check to see if any of the functions in any of your final UC sets overlap y sub c. If they do, then you need to revise that UC set by multiplying the whole UC set functions by the smallest degree, smallest power of x that will eliminate the overlap. Now that's a mouthful. It's easier to show than it is to do. You should have already studied this technique, so this is a review rather than learning it for the first time. All right, so in example 6, we have a second order differential equation, which will make the left side much easier to deal with. So the auxiliary equation for the homogeneous part still assumes that the form of our solution is going to be y equal e to the mx for each one of the roots of the homogeneous. So we get the auxiliary equation m squared plus 6m plus 5, setting it equal to 0 to solve the homogeneous part, and this will factor as m plus 5 times m plus 1. Setting those factors equal to 0, it's going to give us m equal negative 5 and m equal negative 1. Therefore, the solution to the homogeneous part, which we call y sub c, will simply be written c1 e to the negative 5x plus c sub 2 times e to the negative 1x. Okay, so we will have arbitrary constants for the homogeneous part, but remember, when we substitute y sub c into the differential equation, it makes the right-hand side 0, so it is not a solution to the differential equation by itself. All right, it's only the solution to the homogeneous part. All right, so now let's work over on the right with our UC sets. Okay, so let's start with the UC set for e to the negative x. So if we just list that first UC set, it has to include the function itself, and it has to include any functions involved in the derivative process. Well, every derivative of e to the negative x would either be plus or minus e to the negative x, so I don't need anything else. Okay? Now, if you check, e to the negative x does overlap y sub c because we already have an e to the negative x term here, which means there's no way that a function that has a constant coefficient of e to the negative x would be linearly independent of the y equals c sub 2 e to the negative x term. Therefore, we have to revise this UC set, so we'll just call it S sub 1 revised, by multiplying by the smallest power of x that eliminates the overlap. So x e to the negative x is linearly independent of e to the negative x as well as e to the negative 5x. So that takes care of that problem. All right, then we list the UC set for the next function. These are not just one big UC set. Each term on the right has its own UC set. So the UC set for x squared has to include the function itself, has to include any function involved in the derivative process. So the derivative of x squared would be 2x, we have to include the x. Derivative of x would be 1, so we have to include the 1. Compare that UC set with y sub c. No overlap exists, so we do not need to revise any of these functions. Okay? And then the UC set for x, we could call it s sub 3. It would just have x and 1, the derivative of x in it. But you see, this is already part of s sub 2. So we can basically get rid of that, and we do not have to worry about that UC function at all because it's included in the UC set for x squared. So just to make a little bit more room, I'm going to erase that. These are the only two functions that matter then. And we can set up our guess for y sub p. All right, so we've got the revised UC set function here, and then this one, and this one that have to all be included. So I'm going to write some unknown coefficient a times the first function x e to the negative x. I'm going to leave a little bit of room because I know that derivative will involve e to the negative x. And then we need a bx squared plus a cx plus d to take care of the functions in s sub 2's UC set. Okay? Now, we have to make sure that we find specific constants, a, b, c, and d, that make y sub p a solution to the entire non-homogeneous differential equation. To do that, it must be true that y double prime plus 6y prime plus 5y equals the entire right-hand side. Therefore, I have to find y sub p prime, and once I get this, I'll have to find the second derivative of y as well. All right, so taking the derivative of ax e to the negative x with the product rule, we take the first factor ax times the derivative of e to the negative a e to the negative x, and we get negative ax e to the negative x, plus the derivative of the first factor, which is a, times e to the negative x. And then the derivative of bx squared is going to become 2bx, and the derivative of cx is just c, and of course the derivative of the constants is 0, so I won't need anything else after that. All right, now we want to find y sub p double prime. So again, you're using the product rule on the first factor. Negative ax times the derivative of e to the negative x is positive ax e to the negative x, plus the derivative of the first factor, which is actually minus a e to the negative x. But then we have the derivative of this term above it to do, which is another minus a e to the negative x. So this is going to become minus 2a e to the negative x from a combination of the first term's derivative and the second term's derivative. Now the derivative of 2bx is just 2b, and so those are the only terms that we need. I like to draw a line at this point because the sum of the terms in our differential equation, which said 1 of the second derivative plus 6 of the first derivative plus 5 of the original function, has to add up to the entire right-hand side. So we know the right side's got to become 2e to the negative x minus x squared plus x. Now we do the math on the right, one like term at a time. All right, so remember that these coefficients are being applied to both sides of each one of these equations. So for the x e to the negative x terms, I have 5a minus 6a plus a times x e to the negative x. And when you do that math, 6a minus 6a zeroes out. So that term goes away, and that's good because I don't have any x e to the negative x terms on the left. So this will work. All right, the only x squared term we have is in the first line, 5b times x squared. And then the x terms, we have 5c plus 12b. And then the constant terms, let me write below since I'm out of room, that will be 5d, excuse me, plus 6c plus 2b. So at that point, you want to find the value of a, b, and c by matching up coefficients, okay? Lining up your coefficients. And I did overlook this term, so let me put that part down here. The e to the negative x term actually has a coefficient of 6a minus 2a times e to the negative x. So now we've got them all. We've got the e to the negative x term, We've got the x squared term, we've got the x to the first term, and we've got our constant term here. So to find the values, all we're going to do is match coefficients. So let's start by matching the coefficient of e to the negative x on the right with the coefficient of e to the negative x on the left. So 2 on the left equals 6a minus 2a, which is 4a. Solving that equation gives a equal 1/2. So that's taken care of. Now we're going to match the x squared coefficient. So on the left, the coefficient of x squared is -1. And on the right, the coefficient of x squared is 5b. So solving for b, we get -1/5. Okay. Now we're going to match up the coefficient of x on the left, which is 1. Let me erase this number sign. All right, so on the left we have a 1 for our coefficient of x, and on the right we have 5c plus 12b as the coefficient of x. Now since we know what b is, we can actually solve for c by substituting the value of b that we just got. So I'm subtracting 12b from both sides and then plugging in the value of b. And you have to kind of do a little arithmetic here, but this is 1 plus 12/5, 5/5 plus 12/5. It's pretty easy arithmetic. And so that's going to give you 17/5, but then when you divide by 5, or multiply by the reciprocal of 5, you get c equals 17/25. All right, the last equation, matching the constant term. Get some room to work here. So our constant term on the left was 0, but the number on the right is 5d plus 6c, and as we do this, we might as well substitute the values we already know, plus 2b, and you need to solve this equation for d, which is the only remaining letter. All right, so when you do this math, you can use your calculator to help you with the fractional arithmetic if you need to, but this is going to be 6 times 17 is 102/25, and then minus 2/5 is going to become minus 10/25, getting a common denominator, and then you're going to combine those fractions to get negative, looks like positive 92 on the right over 25. Hopefully I haven't made an arithmetic error. Right, and solving for d, then negative 92/25 equal 5d, and then dividing by 5 will give us the value of d. Now I worked this without a calculator, so let's go back and check to make sure that we don't have any sign errors along the way, because I did get -62, so I may have an arithmetic error here. 6 times, right, we should have gotten the coefficient of x should have been, in our original setup, the coefficient of x was letter b, so we have a mistake for b somehow, and I'm not sure where we did that. All right, let's go back and redo the y sub p from the very beginning and give ourselves a little bit more room, just in case we've got an error. Sometimes you just have to do it when you see that things aren't working out and you can't find your mistake. And since I'm working without a calculator today, I'm kind of trusting my previous work. So let me make a little bit more room over here. All right, so we said we needed a times x e to the negative x plus b times x squared plus c times x plus d. Okay. And the derivative of that was needed. The derivative of that is negative ax e to the negative x plus a e to the negative x. The derivative of bx squared is 2bx, and then the derivative of cx is c, and the derivative of a constant, of course, is 0. And second derivative, we get positive ax e to the negative x minus a times e to the negative x, but because of the derivative of this term above it, we're going to get minus 2a e to the negative x. And then the derivative of 2bx is 2b, and the derivative of c is 0. So that's all that would be in our derivative lines. Now, the differential equation told us 1 of the second derivative plus 6 times the original first derivative plus 5 times the function itself is got to add up to the right-hand side expression 2e to the negative x minus x squared plus x. So the method of undetermined coefficients is simply a technique for finding the specific constants that will make these functions x e to the negative x, x squared, x, and the constant 1 solutions to the non-homogeneous differential equation. So when you combine your like terms, the column of x e to the negative x gives us 5a minus 6a plus 1a. So this is going to zero out. So we won't have any of those terms left. But we will have some e to the negative x terms. So the coefficient of e to the negative x is going to be 6a minus 2a. And then we have 5 times b times x squared. Don't want to forget that term. And then the coefficients of x are 5c plus 12b. And then we have the constants, 5d plus 6c plus 2b. So now all you're going to do is match coefficients to try to find the specific numbers that solve the differential equation. All right, so lining up and matching the coefficient of e to the negative x, we get 4a on the right equal 2 on the left. So that means a is 1/2, and that's what we're supposed to have. All right, so the coefficient of that term is taken care of. Now the coefficient of x squared is 5b on the right, and the coefficient of x squared on the left is -1. So we get b equal -1/5. Okay, then the coefficient of x on the right is 5c. Let me draw a little line to separate our work. So 5c plus 12b, which is -1/5, is equal to the coefficient of x on the left, which is +1. So this is 5c minus 12/5 equals 1, which gives, I'm sorry, yes, that's correct. So 5c equals 1 plus 12/5. 5/5 plus 12/5 is 17/5. So c is equal to 17 over 25. All right, so now all that's left is to match our constant terms. We have a constant on the right, this expression 5 times d plus 6 times c plus 2 times b has to equal the constant on the left side, which is 0. Okay, so we get 5d plus, let's see, 6 times 7 is 42, and 6 plus 4 is 10, so it looks like that was right. And then minus 2/5 equals 0. We need a common denominator of 5. So this is going to give us 5d plus 102 minus 10 is 92 over 25. So it looks like we didn't make any arithmetic errors here. We're getting the same answer both times. So we were good. So 5d equal -92 over 25. And d equals -92 over 125. Okay. So at that point, now you have to go back and look at your original setup for y sub p. What was y sub p equal to? Because you got to plug those numbers into the right places. All right, so we had y sub p equal ax e to the negative x. So that's 1/2 x e to the negative x plus bx squared. Well, the b is minus 1/5, so minus 1/5 x squared plus cx, our c was 17 over 25. And then plus d, and our d constant was -92 over 125. Okay? So all of that was our work in trying to find y sub p. So our final solution, remember, has to include both y equals y sub c plus y sub p. So this general solution has to have all these terms in it. And I'm going to run out of room, so I'm going to have to use my second line. So plus the 1/2 x e to the negative x minus the 1/5 x squared plus 17 over 25 times x minus 92 over 125. All right, and since we checked our y sub p twice, we're sure about those constants a, b, c, and d. Ordinarily, you wouldn't have to worry about that because you would be using a calculator as you worked. I just didn't have mine with me when I was doing this particular video. All right, so hopefully that's clear. Let's go back and review our steps. So the first part of it was solving the as if the right-hand side were 0. So solving the homogeneous differential equation for the values of m. Since we got distinct real roots, we had two solutions, y equal e to the negative 5x and y equal e to the negative x. So we formed our linear combination of those, and that part of the solution is called the complementary function, or y sub c. Then we wrote the UC sets for each of the functions on the right. Each term has its own UC set, e to the negative x, had to be revised because it overlapped y sub c. So we multiplied the functions in that UC set, which is just the one, by the smallest power of x that eliminated the overlap. And that was labeled with the S sub 1 revised, the R there. All right, next thing we did was wrote the UC set for x squared. And since the UC set for x is a subset of the UC set for x squared, that was the last one that we needed. And it does not overlap y sub c, so we didn't have to make any revisions there. Then we made our combination of these functions in the revised UC sets as part of our y sub p guess with unknown constant coefficients a, b, c, and d. Then we found the first derivative, we found the second derivative, we substituted back into the original differential equation to get our constant coefficient equation that sets the right-hand side equal to that linear combination involving the particular coefficients of y sub p prime, and y sub p double prime given in the equation. So you carefully do the algebra, finding those numbers, plug it back in to get y sub p, and then write your general solution as y equals y sub c plus y sub p. So it's not a fast technique, but it's a real important technique. Now this is another example of the method of undetermined coefficients that I wanted us to work so that we would again see what happens when we have an overlap. So the homogeneous part of this, we know if y is equal to e to the mx is the solution to the homogeneous, then we're going to get the auxiliary equation m squared plus 4 equals 0. Or m squared equal negative 4 and m equal plus or minus 2i. So pure imaginary roots, which leads us, of course, to y sub c equals c1 times cosine 2x plus c sub 2 times sine 2x. And I think so we'll have a little bit more room. I'm going to write the UC sets on the right, but I'm going to work with y sub p down here below. So if you look at the right-hand side, the UC set for sine 2x has to include both sine 2x and its derivative function, which would involve a constant multiple of cosine 2x. So if we call that S sub 1, we know the UC set for cosine 2x would be exactly the same. So I really don't need a separate UC function, a UC set, because this is a subset of the one we already have. Right, but we see a problem because both of those functions in our UC set overlap y sub c. So that means we're going to have to revise it by multiplying both of those UC functions by x. That eliminates the overlap. So these are the only two functions that need to be involved in y sub p, because that's all we have on the right-hand side. So our y sub p is going to be a linear combination of those. So we'll use a times x sine 2x plus b times x cosine 2x. And I'm intentionally leaving a little room for the derivatives, because we know we have products for both of these terms, I should say. All right, so thinking of this as a factor of ax times the factor sine 2x, the derivative of the second factor multiplied times the first factor will give me 2ax cosine 2x plus the derivative of the first factor times the second factor, which is just a sine 2x. Okay, again, doing the same thing with this product. The derivative of cosine 2x is negative 2 times sine 2x. So that's what we have for first factor times the derivative of the second, and then plus the derivative of the first factor times the second factor. Each time I do these, I like to try to line up like terms. All right, so y sub p double prime, because this is a second order differential equation that we're going to substitute into. All right, so carefully use your product rule again. 2ax times the derivative of cosine 2x is negative 4ax sine 2x. Then the derivative of the first factor is going to be 2a cosine 2x, but 2a cosine 2x is also the derivative of this term, so that's going to give us a total of 4a cosine 2x. Okay? And that's not lined up, but I don't think that's going to be a problem for us when we get finished. All right, now we're taking the derivative of this term, so negative 2bx times the derivative of sine 2x is minus 4bx times cosine 2x. And then the derivative of the first factor is minus 2b times sine 2x, so that's going to be minus basically 4b sine 2x if we include the derivative of this term above it. Okay? All right, now fortunately for us, the differential equation says 1 of the second derivative, 0 of the first derivative, plus 4 of the original function adds up to give us the right-hand side expression for sine 2x plus 8 cosine 2x. So we expect some of these terms to zero out. And since this whole product is going to be 0, I'm just going to draw a line through it to get it out of my way so I won't get confused. All right, so combining that x sine 2x terms, we've got from the first equation 4a and the bottom equation minus 4a. So that's going to zero out completely, which is good because I don't have any x sine 2x terms on the left. Okay, I do have this cosine 4x term that will not zero out, and I don't have any of those in the first y sub p equation, so I've got to have that. Then the x cosine 2x terms, this is going to be a product of 4b times x cosine 2x, and on the bottom we have minus 4b x cosine 2x, so those are going to zero out. And that would leave us then minus 4b sine 2x for the right-hand side. So now we're all set to match our coefficients. The coefficient of cosine matches the coefficient of cosine. So 4a equals 8 and a equals 2. Then we match up the coefficients of sine. So negative 4b must equal 4, which gives us b equal negative 1. Okay, so remembering the form of y sub p was a times x sine 2x. We're going to have first the 2x sine 2x term, and then plus b times x cosine 2x will be minus x cosine 2x. Once you have y sub p, then you know what to do. All you have to do is go back and write y equal y sub c plus y sub p as your general solution. So y equals c1 cosine 2x plus c2 sine 2x plus 2x sine 2x minus x cosine 2x. That is the general solution to the entire differential equation. Okay, notice y sub c is the only one that has arbitrary constants. Y sub p has to have specific constants, and this whole solving process of finding the first and second derivative of y sub p so that you can plug it back in and make it work is how we get those coefficients. That's why this is called the method of undetermined coefficients. You start out with a reasonable guess based on UC functions. This is the wisest move for making your guess about y sub p. If you make a bad guess, you'll end up with a system involving the unknown coefficients a, b, c, and so on that you can't solve. You might get a contradiction even. So it's very important to set up your UC sets correctly to avoid those kinds of errors. All right, this next method reviews the technique that we use when the right-hand side is not made up of UC functions, and this is called variation of parameters. So if we do not have UC functions on the right, we've just got some generic function of x over there, then we would have to solve the homogeneous part first, as always, to find our solutions y1 and y2, and that whatever technique that requires. If we have constant coefficients instead of functions of x coefficients, then we can set up an auxiliary equation and solve for the roots, and we know what to do. But if we have functions of the x over there, we have to pay special care when we set up our y sub p functions on the right that we do the substitution derivatives correctly. All right, so we're going to assume that we already know how to solve the homogeneous part. Y sub c equals c1 y1 plus c sub 2 times y sub 2. And the assumption with variation of parameters is that the particular solution to the non-homogeneous part is going to be y sub p equals some function of x called v sub 1 times the y1 function plus some function of x called v sub 2 times the y sub 2 function. Okay, and then you have to find the v sub 1 and v sub 2. And there's no particular reason why I typed y sub 2 first and then v sub 2. I think that was just a typographical error, but it's fine. It means exactly the same thing. All right, so then you're going to have to do really a several step process to get the functions v sub 1 of x and v sub 2 of x. The first thing I usually tell my students to do is find the Wronskian. Just do the Wronskian of y1 and y2 separately. That way you'll know that they're linearly independent anyway. And both the formula for v sub 1 prime here and the formula for v sub 2 prime here involve the denominator that is the Wronskian. All right, and then using Cramer's rule on the system of equations that we would get from substituting y sub p and its derivatives back in, we know that the first function, v sub 1 prime, is going to be found by replacing column 1 of the Wronskian with 0 on top in row 1, and then f of x divided by a sub 2 of x in row 2. Very important to remember the divided by a sub 2 part. If that's a constant coefficient of 1, then you won't have to worry about it. But if it's anything else, including sometimes Cauchy-Euler differential equations that might have x squared times y double prime, you have to use that here. So that function of x, that is the coefficient of the highest order term, that goes in the denominator under f of x. Okay? Then you find the determinant on top, divide it by the Wronskian, simplify as much as you can, and then integrate to find v sub 1. Okay, then you're going to do the same process to find v sub 2 prime, except you replace column 2 of the Wronskian with 0 in row 1 and in row 2, the f of x on the right side divided by the a sub 2 of x coefficient of y double prime in row 2. And then that whole thing is divided by the Wronskian. Once you simplify v sub 2 prime, then you're going to integrate it to find your v sub 1 of x function and your v sub 2 of x function, both will be known to you. Once you've got that, write y sub p, going back to what was your assumption, and then simplify if possible. There is no guarantee that y sub p in this form will be linearly independent of y sub c. So sometimes you can eliminate terms on the right that are already included in y sub c. They're just not needed both places. Okay? All right, let's look at an example of using variation of parameters to do the problem in example 8. Notice the right-hand side function, secant 2x, or secant squared 2x rather, is definitely not a UC function. The derivative of secant squared 2x is 2 secant 2x times the derivative of secant 2x, which would be 2 secant 2x times tangent 2x, and it just gets uglier and uglier every derivative. It does not have a finite set of functions involved in the derivative process. All right, so we begin by finding the solutions to the homogeneous part. At this point, you should probably have some of these memorized because we've done a lot of the same ones. So m squared plus 4 equals 0 is going to give us our m equal plus or minus 2i, which we know will give us the complementary function y sub c equals c1 cosine 2x plus c sub 2 sine 2x. We're going to assume the solution to the non-homogeneous part is some function of x, we'll call v sub 1 times cosine 2x, plus some function of x we'll call v sub 2 times sine 2x. All right. So the next thing we're going to do is find the Wronskian of those two functions, which, if you remember from the first slide, is simply a determinant of a 2 by 2 matrix. These functions in row 1 and their derivatives below in row 2. So the derivative of cosine 2x is negative 2 times the sine of 2x. Derivative of sine 2x is 2 cosine 2x. So when you do your left diagonal product, you get 2 cosine squared 2x. 2x, I keep leaving the 2 off. And then minus the right diagonal product, remember to negate it, will give you plus 2 times sine squared 2x. If you factor out the 2, you get 2 times cosine squared 2x plus sine squared 2x, which from our Pythagorean identity, we know that's equal to 1 inside the parentheses. So this is just a Wronskian equal to 2. But we do have to remember that. All right, now, to find v sub 1 prime, we're going to take the Wronskian and replace column 1 with the 0 and the right-hand side functions. Right? So our right-hand side was secant squared 2x, and we don't have a coefficient in front of the y double prime term. So that means all we need here is 0 secant squared 2x. But in column 2, we need the same column 2 that we had in our Wronskian, sine 2x on top and its derivative below. Okay, this diagonal product is 0, so it'll go away. Minus the right diagonal product gives us negative sine 2x times secant squared 2x divided by 2. And you kind of want to set yourself up to be able to have this written in a form that you'll be able to integrate. So since I know secant 2x is 1 over cosine 2x, let's pull out the negative 1/2 and rewrite sine 2x times secant 2x as sine 2x over cosine 2x. And then that would leave us a secant 2x. Not secant square x. I misread that. Let me correct that. Secant 2x, because we got rid of the squaring when we took the 1 factor of secant and we wrote it here. So this is actually v sub 1 prime. Let me get down a little bit. V sub 1 prime is equal to negative 1/2 secant 2x tangent 2x. and we need the integral of that. And if you think about what function has a derivative of secant u tangent u, then you can find this integral pretty easily with a u substitution, letting u be 2x. So you're going to get negative 1/4 secant 2x. And you can certainly check that by taking its derivative to make sure that you've got your constant coefficient right. Okay? All right, now we're ready for v sub 2 prime. Now, by the way, this determinant that we used in the numerator, some people will label that w sub 1. So if that helps you, w sub 1 divided by w is how you're setting up the fraction that's equivalent to v sub 2 prime. All right, now v sub 2 prime. Well, that's going to be w sub 2, replacing column 2 at the Wronskian. So we had cosine 2x on top there, and its derivative was negative 2 sine 2x below. And column 2 now becomes 0 secant squared 2x. And that whole thing is divided by our Wronskian of 2. Okay? So this is a little bit easier because the left diagonal product is cosine 2x times secant squared 2x. Well, that's just going to be secant 2x because cosine times secant is 1. They are reciprocals of each other. And when we integrate that, v sub 2 is going to be 1/2 times the integral of secant 2x, which is 1/2 ln absolute value secant 2x plus tangent 2x. I don't need to worry about arbitrary constants in this process, remember. I'm looking for a specific solution. So I can let my constants of integration be 0 here. All right. So once you've got v sub 2 and v sub 1, which we do have, then we simply go back and we plug those in to get y sub p. So y sub p, remember, was v sub 1, and this was v sub 1 right here, the negative 1/4 secant 2x multiplied times cosine 2x, which was my y1, plus, and then all of v sub 2, 1/4 ln absolute value secant 2x plus tangent 2x times the second function, y2, which was sine 2x. Okay? And then your general solution is going to be written y equals y sub c plus y sub p. Now, if you look at this product, secant 2x times cosine 2x is equal to 1. So all that's left here is negative 1/4 times 1. So our y sub c, c1 cosine 2x plus c2 sine 2x, that's what we started out with, is now added to our simplified y sub p, which is minus 1/4 plus 1/4. Let's put the sine 2x in front. I think it would be a little bit less likely to be misunderstood, times ln absolute value secant 2x plus tangent 2x. And this is the solution using variation of parameters. So that technique involving determinant divided by determinant to find v sub 1 prime and v sub 2 prime works really well if the right-hand side function is not a UC function. Sometimes you get ugly integrals, but this is really the only place where there's a great deal of integration in the process for solving the differential equation. All right, now the Cauchy-Euler differential equation techniques vary from book to book. My favorite technique is a substitution technique that requires that we let x equal e to the t, which would be equivalent to saying t is equal to the ln of x. And remember, using the chain rule, we know that the product of x times y prime, x times dy dx, becomes dy dt when you use the substitution. And we're not going to prove that. We're just going to assume we already have. And then the product of x squared times y double prime in this one can be replaced with the difference of the second derivative of y with respect to t minus dy dt, again, coming from the chain rule. So our goal is to take the entire differential equation that has y's and x's in it, with y the dependent variable, and rewrite it in terms of y with t as the independent variable. If it's a non-homogeneous differential equation, you want to go ahead and rewrite both sides of the differential equation in terms of t. It's going to be so much easier to use this technique than the technique that some books use for substituting y equal x to the n. With a homogeneous differential equation, either way is about equivalent amount of work. All right, so the technique, substitute, rewrite in terms of t, solve that differential equation for y as a function of t. Of course, if it's non-homogeneous, you'll have a y sub c part with a e to the mt types of equations and a y sub p part with t as the independent variable. Rewrite your entire y equals solution as a function of t, and then go back and get rid of the t's using the original substitutions that we did. Right, so I really like this technique, and I'm going to use this technique on example 9. Okay? All right, so the substitution, x equal e to the t, I always like to write that down because otherwise it's hard to follow your work. All right? So the left side, x squared y double prime, now becomes second derivative of y with respect to t minus dy dt. So that's the first term. So that replaces x squared y double prime. Okay? If there were a coefficient in front of that x squared y double prime, remember that that coefficient would be outside the parentheses and you'd have to distribute that back through. Next, we take the derivative of x times y prime, which becomes simply dy dt, according to our substitution rules from the chain rule. And then plus 6y, that's no different, equals. Now, remembering that x is being replaced with e to the t, the right-hand side is now 4e to the t minus 6. So if we simplify our differential equation, we have the second derivative of y with respect to t minus 1 dy dt minus 4 dy dt is minus 5 dy dt plus 6y equal 4e to the t minus 6. Now just completely forget about the original function having been in terms of x and solve this. Solve this differential equation. So here we've got a, the left side has constant coefficients. If we assume that the solutions to the homogeneous part are of the form y equal e to the mt, because t is our independent variable now here, remember, then we would get the auxiliary equation m squared minus 5m plus 6 equals 0. And that factors as m minus 2 times m minus 3. So we would have two distinct real roots, the m equal 2 and the m equal 3, which would lead us to the y sub c equals c1 e to the 2t plus c sub 2 e to the 3t. Leave that as it is until you get the entire solution to this differential equation. That's the one we're trying to solve right now. All right, so we look at the right-hand side. E to the t has only itself as a UC function set, and 6 would have a constant 1, and neither of those overlap y sub c. So this one, I'm just going to go ahead and write y sub p as a times e to the t plus b times 1, because that's all that would be involved anyway. First and second derivative. First derivative is a e to the t, derivative b is 0, and then the second derivative is also a e to the t. And this differential equation that we were working with says 1 of the second derivative minus 5 times the first derivative plus 6 times the original function has to add up to the right-hand side 4e to the t minus 6. So when you do that math, 6a minus 5a is a plus a gives me 2a e to the t. Okay? I always like to check that step so I don't make any arithmetic errors. And then plus 6 times b is all that's left. So matching our coefficients of e to the t says 2a equal 4, a equal 2. And matching our coefficients that are constants, 6b on the right equals the negative 6 on the left. So b has to equal negative 1. And that means y sub p is a 2 times e to the t plus the b, which is plus a negative 1 or minus 1. And then our general solution in terms of t here is just y equals c1 e to the 2t plus c sub 2 e to the 3t plus the y sub p 2 e to the t minus 1. So now all you have left to do is rewrite this in terms of x, because the original variable was x. Remember, x equal e to the t. So this first term is going to become c sub 1 times e to the t squared, which is just x squared. The second term is c sub 2 times x to the third. This is going to be plus 2x minus 1. And the advantage of this technique is you usually will not need variation of parameters because you're keeping everything in terms of t. So unless this star differential equation right here, unless this differential equation has a right-hand side that's not made up of UC functions, you will not need to use variation of parameters. So that is the method that I would recommend. I have found very few times do I need to use variation of parameters. So I'm going to stop there for today, and we're going to use that technique is the one that I would recommend. I did have another slide ready for doing the other method, but I think you're going to be smarter to just stick with this technique. So hopefully when you review this video, you'll be able to go back and complete the rest of your review and work some additional examples on your own without assistance from Mrs. Solomon. If not, contact your instructor for further assistance.